So, hello everybody. My talk actually has two purposes. One is more or less educational, because it's a bit surprising to me, but not like everybody in the Python community cares about performance, or not everybody knows how to, so for those who do care, not everybody knows how to find the problems. So I will give some overview of what's available right there in the market, be it free version or maybe some proprietary. And then I will be showing the prototype that we at Intel we built. So that should address the problem of profiling stuff. So I think almost everybody have a seat now, and I should proceed further. So first things first is some legal notice, you know. I have to put this slide in on some legal stuff, you know. I won't go reading it. So you can read later if you want to. Just about, you should have to remember that not every benchmarks are equal. So just have to tune for your workload and keep that in mind. Anyway, the agenda of current talk is, why do we need Python optimization? Like, you may hear someone saying, I have my Python program and I'm happy. So maybe it's the case or maybe not. And then, if you are the one who needs to optimize Python code, how do you find which places in your code you need to pay your attention to? I think someone in the talks previously said about the Pareto rule, like 80% of efforts only yield 20% of stuff, and vice versa. So you should concentrate on some 20% of your code to get the best results. Then, as I said, an overview of existing tools, and a really simple, you may call it dumb example of a typical mistake, and how certain tools will show you where is the problem. And then some prototype capabilities and stuff, which I'm showing off, and some Q&A, right? Now, why do we even need to optimize Python code? As we're at the Python conference, probably everybody is aware that Python powers a wide range of software, like applications of web server, like some small scripts for automatization, a whole bunch of stuff. And some of those implications are those where performance matters. For example, if you are creating a web server, which should handle quite a big load, you do care about the performance of the server. The other problem is Python is actually a very good language to start with. It's easy to learn, and it's pretty forgiving, so you can make some mistakes and you won't notice that unless you give it enough load to churn on. So then, and sometimes you're just not happy with the speed of your code, or the reverse, maybe your customers are not happy with the speed of your code. So I think that probably for everybody who came here, it's pretty obvious that there are times when this performance of your code matters. So it's just the question, how do we find out how to optimize the code? Now, you can see that probably the first thing that comes to mind, you can just stare very hard at your program and think, maybe this line is slow, or maybe this function is slow, or I know I should not use this list comprehension. The problem with this approach is it's often wrong. As I think that PyPy guy said, not everybody understands how the interpreter works. I won't claim that I understand every little bit. I probably understand something, but certainly not the whole bit of very intricate details of the interpreter. And I don't think anybody can say that he does understand it, because the interpreter is big. Then you can, input put some print statements with some timestamps to see if this function is taking long or this function is taking long. And that should be okay for some workloads. For example, you can monitor your, say, the web server and see if some request is taking long or not, like some logging, some metrics and stuff. The problem with that is if you don't have this logging in your application already, and you need to find a bottleneck somewhere in your code, you have to write a lot of logging stuff in your code just to find this little bottleneck. Hard to do. Then there is a solution that I'm leaning toward, and I think I'll convince you that you should use that solution. It's called profiling. So you know, in computer science, profiling is just gathering a set of metrics. If you want to find out this way or this way, what your program does. And right now I'm concentrating on profiling the CPU time. So how long does your program run, or how much CPU time it consumed, right? The problem with this profile approach is you need some tools. For the hardware approach, you probably just need a text editor, and that's all. For logging, more or less the same. You probably need a tool to process the logs, but you can code it yourself like in 5 minutes. With the profiling, it's a bit harder. And then again, not all profilers were born equal, you know. There are different techniques out there. The three that I find the most widely spread are event-based. That is when something happens, like function started or function ended. There is an event fired, and the profiler can capture this event and store some information about that. There is the easiest example is Python built-in cProfile. The events it watches for is entering and leaving the function. Then there's instrumentation-based. It usually requires you to modify your application. The example for Python would be line profiler package, which can tell you which lines of your function are slow, but it would require you to annotate your code with decorators. And then there is statistical profiling or sampling profiling, which basically means that you take a sample each given period of time to see what your program is doing. And an example, I'm from Intel, so I'm going an Intel example. It's Intel VTune amplifier. And this approach is good enough because it's usually accurate enough. See, it's not the exact call tree you are getting, but some approximation. But it's usually way less intrusive for certain cases, like very many functions which are very small. Each function is very small. Now, let's see. I have a typo. Just ignore it. I have the table that compares some tools that are over there. Like I said, cProfile. It's a pretty good start point because it's in the standard library. It has a text mode UI called pstarts to work with the results, again built in. And it has some GUI viewer called runsnakerun, and it's open source and stuff. The problem with this is it profiles to the function level. That is, it cannot show you which part of the function is slow, only that this particular function is taking way much time. And its typical overhead is from 1.3x to 5, usually around 2x. That is, your program under the cProfile usually runs 2 times slower than without it. Then there is the Python tools. You know, Python tools from Microsoft. It's even open source. The problem with it is it's again only function level. Its overhead is about 2x, and it's only Windows as far as I know. Though the Visual Studio itself offers some remote profiling, Python tools, I think they don't. At least I wasn't able to find how to do. Then there was, you know, the guys with the PyCharm. They recently introduced the support for cProfile. I find that their UI is pretty good. The problem with that is again cProfile based. Oh, you can base it on YAPP. Well, YAPP is basically cProfile made thread aware. So you can see which threads are taking time, but no line level information. Then there is line profiler package, as I said. It provides you with line level information, but the overhead is, oh man, up to 10 times or more. There are some more statistical profilers out there, less known, like statprof and plop, Python low overhead profiler, and the new coming, the vmprof from the PyPy team. I would say that the problem with them, they kind of share, is the UI is not very intuitive to work with, and it displays this or that. But at least in the plop and the statprof, and I think in the vmprof too, I cannot find the way how to find this certain line that's taking time. Right? Now, let's see. So this is a simple module that has two functions, right? The one which is slow is written with a simple, typical Python beginner's mistake. Now, who knows which mistake is that? Yeah, string concatenation, right. And the reason for that be, anyone knows? Sorry? Yeah, the thing is, strings are immutable, so you have to create a new string each time. That requires you to allocate memory, copy stuff there, and deallocate the old one. A lot of work. Now, for the first version, it actually doesn't do any memory allocation or copying until there is one last join. And that join does only one allocation and one copying. So basically, the first approach is something about the n square, and the second one is more or less linear. Now, the sample program to test this module is just very, very simple program, runs slow and runs fast. And I took some figures on my laptop. They vary from time to time because laptop can be doing something not that I can control of, like, you know, some antivirus software kicking in or stuff, but still. You see that the slow version is about 3 times as slow as the fast version. And we use this as a basement, as a baseline, because there's no profiling, or profiling by login, but no tool. So we use it as a baseline. Now this is how cProfile works and how pstats look like. You can try to figure out which functions are slow. So if I have my mouse, you can see that this function is slow and this function is like 2 times faster, right? But just imagine that you have not 10 functions, but you have a very, very, very big program that has like 10,000 functions. Oh man. And if you're looking not at the top 10 hotspots, but probably something more intricate, it's kind of hard to work with this UI. And as I said, the overhead here is, well, on that particular example, the overhead is pretty okay, but still around 1.5. Then, as I said, there's a UI. Not that good looking, I think. If there's anybody who develops this stuff, forgive me. But, you know, let's just go further. This one looks much nicer. This is PyCharm. The numbers might not be easily readable because they're gray, but overall, the stuff is pretty similar. And we can have this line profiler thing, the only one that easily does the line-by-line results. And as you see, the overhead starts with 2 and a 6, and for the first one, it's actually 8x, and it ended up slower than the slow one. So this line profiler thing is not that easy, right? And let's just imagine that we have a program that runs for, say, 2 hours, and to wait for it in 10 hours to complete. No way. Then there is Python tools. The UI is, well, I would call it okay. One problem with the, or maybe not problem, but the for someone it might be a good thing. It measures not CPU clock, but wall clock. That means you won't know how much CPU time your function had consumed. You would know how much time passed. The wall clock is the thing that ticks like a clock on a wall, you know. And as they say, the overhead is not that small, and so the problem with all those with big overhead is that overhead is not only making you wait longer. The problem with the overhead is it influences the run of your program, so it can skew your results. So if I flick back a slide, this one, you see that the overhead skewed the fast results way too much. Because we remember that the slow version was 3 times slower than the fast one, right? Without the profiling things. And now I have some slides prepared that show the prototype, but I think it might be just nicer if I give you a live demo, right? So here goes. Just let me take, so this is, to the right side. This is the window, right? And I'm just, creating a project just for the sake of completeness, to be easier, this way. I'm just going to duplicate. Okay. So let's say that it's a demo EP 2015. I create a project because I'm hoping to do several analysis, like I want to figure out if my code, that I changed something, if this change was good or bad, right? Then I just say, I want to profile Python. It finds that one is in my path. Then I just add the path to my Python script. Please remember this is a prototype, so you can see some namings there, but it's a prototype, so it's not out in the market ready. And I just take the same example of run.py, and I say that I wanted managed code, because Python is managed code, obviously, not native one. Then I say I want Python hotspots, and I run a program, and this program runs for some time. The thing with this profiler being different is, as I said, it's statistical one, so it should not influence the program very much. Oh, there you see, the slow version took 20 seconds, and fast version took 5 seconds. And that's pretty on par with what cProfile have, I think. So you see that we have 2 functions that are named top hotspots. For example, I want to look into the slow function. I click on it. It opens in the bottom-up view. And there is a nice timeline that shows you how much time was spent during the program run. So for example, if you want to fine-tune some exact portion of your program running, for example, if you're writing a website, there might be times when you have some dozens of requests, and there are times when you have none. So we can just select the time when you have lots of requests and see a hotspot. And now I double-click the function, and it opens me a source view, showing that, indeed, those guys were right. It's the plus equal thing, which took all the time. Now for some threaded thing, because I find it to be what's lacking most in other profilers, is most of them are not thread aware. That is, for example, cProfile. If you try running a multi-thread program with cProfile, by the way, anyone tried? Looks like nobody. Nonetheless, if you try running it with cProfile, you won't be able to find out which thread consumed certain times. You just see the results of the functions one by one. You won't be able to figure out which thread was slow and which thread was fast. And with this prototype, you would see that you can filter by threads, you can filter by time, even by module. So if you're interested in functions in a certain module, you're able to do that. So let's see. Here's, you see the three threads. One was actually spinning, and one was doing the setup work, you see here. This one, this small one. And the last one was just waiting. So what I think is kind of amazing if I click here in terms of how Python works, I'll just show you, right? Here are actually 2 lines taking time in this cycle. So the program is pretty simple, just calculate the time and just actively wait for it to pass. And the interesting thing here is that even pass statement costs time. You know, that might be something not obvious, but every statement in Python, even pass one, might cost you time. So if you're, for example, waiting for something, you should use some synchronization primitives or stuff, not just spinning on spot. So you see here there's a call stack, the full call stack for the function, so I can drill down to the threading PY if I want to for some reason. There's not much interest in there, just a function. So let's see. I have, let's continue with my talk. Okay. What's this? Why is this below? I have no idea why it's below. Let's try again. Man. Okay. Stuff like that happens all the time. Yep. Here we go. So I've just skipped the slides with the screenshots. I think we showed something in the demo. So to summarize things up, the prototype has this line level information. It could show you which lines of Python code are taking time. And I measured the overhead on several benchmarks, including the Python Grunt Unified benchmark thing. Well, it sounds scary, but it's actually the default benchmark for the Python distribution. And the overhead is, I can say it's not that small, but it's pretty decent. And it supports, right now it supports Windows and Linux. It supports 32 and 64-bit Python. Supports, you can read the slides for you. It supports, in a way, it supports some remote collection. For example, if you want to profile a script on remote Linux box, you can do so using the SSH. And I think I demoed that the UI is, well, at least I do like the UI. I find it quite easy to use. Well, if you want me to add some spice, the way which I ended it with this prototype was I was working on a build system, our internal build system, and I was wondering why it was so slow. So I came up with this prototype, and then I came up with how to integrate it with our current software, and then I started learning to use this software. So not the other way around. Anyway, also there is an interesting thing that I didn't show you. It might be a bit harder to show in a quick demo, but there are actually 2 workflows supported. So one is that I've shown, you can start an application and wait for it to finish or stop it if you are bored with it. And another way is you can attach to a running application, profile for a time, and detach. That I find especially useful if you want to profile some server code and you don't want to bring down the thing for maintenance or something. You just attach to the live server, perform some profiling, and then detach, and server continues on, like you didn't interrupt it. So here's the comparison table. I find the results are okay. At least what I do care about is line level information and low overhead. That should not skew your results so much, right? And so there's some summary of our internal usage, because you see this tool is not in the public yet, so sorry, no quotes from the customers. But as I said, We used it to fine-tune the one web page in our internal Bilbao installation. By the way, Bilbao is open source, and I personally find it an awesome project for making your distributed scheduling system, scheduling tasks. And this is where the attach profile detach thing shines. So you just attach to your running master, like people just continue using it, you attach, try some web pages, try some load, and you detach, and just nobody notices that you did some profiling. And I was able to speed up a page by 3 times, like from 90 seconds to 28. It was not very easy, I had to rewrite stuff a bit, but still. Then there was a report generating thing in our internal stuff, which was written more or less along the lines of doing how I show you the demo, like concatenating strings, and it worked okay for log files like 10 kilobytes long, 50 kilobytes long, but when we tried it on a pretty small log file, about 1 megabyte, you see the results. It was over 300 seconds, and we were able to speed it up to 2 seconds, right? And then, as I said, scones-based internal build system. There were numerous places where we applied it, and in most of all, we achieved some results like maybe 2 times increase or 50% increase. Not something that you can pass by. And now some, some screenshots again. But this is open source stuff, the Chromium JIP project. I think they are getting away from that, but anyway, just to show that it could profile multiprocessing thing, like this JIP script was spawning multiple processes and all were captured. Then some NumPy-based code that just shows you how you can apply this to a code that works and does a lot of stuff natively. This np.dot function is a native function, and you see that it uses a lot. So probably this is a good example of your Python program. When you glue stuff together, you want to be doing a lot of, as much as possible in the native code, and keep your Python program as simple as possible. And now, kind of some advertising. So if you want to give a try for this with this tool, you can either subscribe at scripting@intel.com. We're also making a proof of concept work on speeding up the Python interpreter and NumPy, SciPy libraries. Sign up. Or you can catch me or my colleagues at our table or during sprints. Then there's some free software if you qualify, like if you're an academic researcher, or most certainly if you're an open source contributor, you can get some Intel tools free. You don't need to remember that link, just Google free Intel tools. It's like first or second link. And time for questions.
So you're a statistical profiler, but all the other ones you compared it with were not statistical profilers. So you can make the overhead of a statistical profile arbitrarily low, though, can't you, by just reducing the amount? So how does it perform compared with the other statistical profilers?
Well, this table I've shown you, yes, it's event-based profilers. Those are just mostly known. The other ones you have to figure out how to find. And I don't have the figures on me, but probably, well, the vimprof says that they have like 5 to 10% overhead. And plop says they have like 5 to 10% overhead. And our typical overhead is, I can say maybe some 10 to 20%, but you get line level information. They don't show you that. At least they don't show that. Probably they do collect it, but they don't show you that.
We had a question at the back, right? Yes. So maybe you spoke about it, maybe missed. So any chance you will release at least part of this profile as open source? Yeah, I know, sir. It's Intel, but
You know, you don't think that Intel does everything does closed source. The plans for this exact profiler are not final yet, so I cannot say if it would be made public or not. But if you're interested in Intel's open source stuff, first of all, there's 01.org stuff. It's Intel one, and we are doing a lot of contribution to the open source, like Python contribution, like speeding it up, and those, like speeding up the interpreter itself, would definitely make it to the open source.
So you've shown that your profiler can show the lines, the Python lines that are consuming the most.
Mm-hmm.
Can you dig more into the details and see which libraries they are calling behind the scenes, or just show the assembler in the interface?
The problem with Python here is that the standard cPython, you have no idea about the assembler. So it's just an interpreter, nothing is compiled. So you cannot show the assembler in that. I think what you're asking, asking for is to show some native frames, like native functions down below, right?
No. I am talking about what's being executed behind the scenes. So, for example, cPython is executing something, right? I mean, for example, in the first example that you showed, that the problem was the string that was copied a lot. So probably there is a memcpy called behind the scenes, right?
Yeah, probably that.
Mm-hmm. So this is my question. It is a way to see which libraries, function libraries, are called?
Yeah, as I'm saying right now, probably what is going to answer your question is if we have a stack that Python frames would be, you can see what native functions were called, like this memcpu. Well, that's certainly planned, but it's not there yet. But if you sign up to this program, I think it will eventually be there. At least I hope so.
Thank you.
More questions? Right.
On your slides, you specifically mentioned Python 3.4 that you support. Is there a problem with older ones or newer ones?
What I did mention is actually the stuff I just tested against. So my guess would be it should work with 3.5 and probably with 3.3 and maybe with 3.2. I'm not that sure. The thing is, we are not bound into certain Python version, so we need to be able to use some API that is kind of stable. So it's not something that's compiled in your interpreter. You just can pick any interpreter you have, like install something maybe from Anaconda, from ActiveState, from Python.org, or maybe even embed a Python into your own application, and it is still possible to profile it.
More questions?
My guess would be it even should work with 2.6, but who cares about 2.6?
Okay, good.
Will it also show function names of C extensions I call into from Python?
So let's flip a bit of slides. Probably if you look at the example at the very right, this dot is actually a C extension function from the NumPy, the one that's highlighted here, like this one. So you see that this line calling the native function took almost 2 seconds. So it is within that function. But for now, you won't be able to see down below which stuff was there. As I said, it's sorry, it's planned, but it's not there yet.
Hi. Is there a way for your profiler to work with PyPy or other Python interpreter, or is it just working with the Python?
Right now, the techniques involve using C API that is exported from the Python library. So as for some other Python interpreter that just follows the C API, it should be possible, should be. With the PyPy, it's a bit different because PyPy does JIT compilation, and there are not that much calls of the functions that are of interest. So probably it won't work with JIT mode. That's why you have vmprof of those guys for.
Right. More questions? I've got a small one. So this is optimized for CPU time, but
Yeah.
Is there a way to have a similar tool for I/O that would like statistically look at into S-trace or something?
Yeah, that's an interesting question, and it's something I hear from time to time. There is a way, obviously there is, because when there is a problem, there is a way. And I think that the platform that we are basing on, the VTune stuff, has the solution for native code. So I sure hope that it would be planned that we do something for Python. I can be that sure because it's not yet planned, but it's something I have in my mind.
Okay. Couple of last questions. Right. So thank you again, Vasilij.
And one last minute note, everybody, so if you are interested, again, just either sign up there or come to our table or catch me during sprints. I can give you a hands-on there. Thank you.